Welcome to the session. So today I am here to explain balanced binary search trees. In the yesterday's session, in the last session, we had discussed about expression trees and how to sort the given unsorted array by using heap sort technique. So today we will go for balanced binary search trees. So before going to balanced binary search trees, first of all, why we are using balancing term, where we are identifying this kind of problems, we want to discuss now. Then we will move to balanced binary search trees. So first, suppose I am given an elements like this 1, 2, 3, 4. 1, 2, 3, 4. Okay, so here the given elements are in sorted order, nothing but ascending order. So whenever we want to construct a binary search tree for the given set of elements, what to do is, say the first 1 is identified as root node, 1 is identified as root node, the next 2, so the 2 is inserting as a right child or right position to the 1. Why? Because according to the binary search tree, so comparatively root node, lesser element as a left child, greater element as a right child. So comparatively 1, 2 is greater, so that's why it moves right position. So that's why it inserts as a right child. So whenever we want to insert 3, comparatively 1 greater, comparatively 2 also greater, so 3 is inserted as right child to the 2 parent node. Suppose whenever we want to insert 4, okay, in that case also the 4 is inserted like this. So this kind of trees are called as skewed binary trees. Here this is called as binary search tree, nothing but skewed binary search trees. Skewed means what? So each and every time the right subtree only is presented, left subtree is null. Means there is no left child here, there is no left child here, there is no left child here, there is no left child and right child here. So the majority of the nodes are inserted in only one direction, that is the right direction. So this kind of trees are called as right skewed binary trees. Similarly, we are taking the elements in a reverse order, nothing but descending order, we are getting left skewed binary trees. Okay, so what is the problem? This kind of trees. What is the problem is happened with this kind of trees? So whenever we want to search an element, say 4, generally we know that the binary search tree gives the time complexity for search operation is big O of log n base 2. Binary search tree gives the time complexity for the search operation big O of log n base 2. Okay, but in this case, first we are comparing with 1, move to the right position. Comparing with 2, move to the right position. Comparing with 3, move to the right position. Comparing with 4, yes, element is found. So 4 comparisons are required. In this way of construction of trees, suppose in this case, nothing but skewed binary search tree case or skewed binary tree case, whenever we want to search an element in the tree, it gives the time complexity is big O of n. This is one time they are asking the question, what is the worst case construction of binary search tree? This is the worst case construction of binary search tree. Whether it is a right skewed or left skewed, these two are called as worst case construction of binary search trees. In this type of trees, what is the problem is to search operation, the search time operation time complexity is too high, means the time complexity is big O of n. So that's why we need to go for balanced binary search tree. Means we need to balance this kind of trees also. Balance means left side nodes are there, left subtree is there, right subtree is there. Left subtree is there, right subtree also there. Okay, so what are the different kinds of balancing in case of balancing? So the first one is AVL tree. The first balanced binary search tree is AVL tree. This is in your syllabus. Okay, means in the next 5 minutes onwards we will discuss this concept only. The next one is red-black trees. This is in your second semester. The next one is B trees. The next one is splay trees. So these are all called as balanced binary search tree. Balanced binary search tree constructions. Okay. So this is only in your syllabus. These three are not in your syllabus. These three are we will discuss in the next semester in the advanced data structures subject. So first we will move for what is AVL tree. So AVL tree. Another name for AVL tree is balanced binary search tree. Balanced binary search tree. So here three AVL, how we are getting the name like this is three different scientists. Adelson, Walensky, Landis. Okay, these three are the three different scientists' names starting letter AVL tree. So, what is an AVL tree? What makes the difference in between binary search tree and AVL tree with respect to the definition part? With respect to the definition part. Okay. So, according to the binary search tree, comparatively root node lesser element as a left child and a greater element as a right child. So, AVL tree is also a balanced binary search tree. In addition to that, the balance factor BF is nothing but balanced factor. Balanced factor. How to calculate the balanced factor? Means height of the left subtree minus height of the right subtree is called balanced factor. Okay, say for example, here 1, 2, for the previous only, 3, 4. This is the tree in the previous example, right? So height of the left subtree 0, height of the right subtree 3. So 0 minus 3, minus 3 here. The balanced factor. Here, height of the left subtree 0, height of the right subtree 2. So balance factor is minus 2. In this case also, the balance factor left subtree is 0, right subtree 1. So minus 1 is the balance factor. In this case, height of the left subtree 0, right subtree 0. The balance factor is also 0. Right. So the AVL tree is also a balanced binary search tree, and here the balance factor values are only minus 1, 0, 1 are only allowed. The tree consists of the balance factors as minus 1, 0, 1 at each and every node. At each and every node, the balance factor value is either minus 1 or 0 or 1. These three balancing factors only allowed. Such type of trees are called as AVL trees. Such type of trees are called as AVL trees. Okay. So, how to construct an AVL tree? The next part is how to construct an AVL tree. Okay. So here the maximum difference is 1. Maximum difference is 1. Minimum difference is minus 1. That's why this is called balanced binary search tree. Say for example, we will take, well, operations are common. What are the different operations? What are the different operations in a AVL tree? Means same. Insertion operation is there. Deletion operation is there. Search operation also there, in addition to the traversals. In addition to this traversals. So these are the three different kinds of operations. Till now what we discussed is what is the difference in between binary search tree and AVL tree is AVL tree is also one kind of binary search tree. Nothing but balanced binary search tree. And here the balance factor values are only -1, 0, 1 are allowed. Such type of trees are called as balanced binary search tree and nothing but AVL tree. AVL tree. And what are the different kinds of operations is insertion, deletion, search and travels. These are the 4 different kinds of operations in AVL tree. Next, so how to perform an insertion operation here? How to perform an insertion operation here? Insertion operation phase 1 is doing like binary search tree only. Say for example here, same example I am taking. First I am taking a simple example. Later I will go for a complex one. Later I will go for a complex one. Say, so 1, 2, 3, 4. 1, 2, 3, 4 means here step 1. Step 1 means whenever we are inserting an element, first element. Okay. So automatically the first element is a root node. No doubt. So 1 is inserted in the binary search tree and the balance factor is 0. Why? Because height of the left subtree is 0. Height of the right subtree is also 0. Next, whenever we are inserting a second element, so comparatively 1 to 2 is greater, so it moves in the right direction. And again we need to compute balance factors. So here the balance factor is 0, here the balance factor is -1. Why? Because height of the left subtree is 0, height of the right subtree is 1. So 0 minus 1, minus. So 0 minus 1s are allowed. Okay. Next, step 3. We want to insert third element. So 1, 2, and we are inserted as 3 like this. So whenever we are computing the balance factors, 0, -1 and -2. Height of the left subtree is 0, height of the right subtree is 0, 0 minus 0, 0. Height of the left subtree is 0, height of the right subtree is 1, 0 minus 1, -1. Height of the left subtree is 0, height of the right subtree is 2, 0 minus 2, -2. So this is the way to compute balance factors. Right? Balance factors. So here, for balancing this tree, we need to do some rotations. For rotations also some cases are there. Later I will explain in brief. First, what kind of case it is means in the right subtree I am inserted as a right child. Here we are missing the balance. Why we are missing the balance is in the right subtree as a right child I am inserted. That's why I am missing the balance. So that this is a RR case. RR means right subtree as a right child. So RR is a single rotation case. In that case, just we are moving towards to left direction one time. Means that what is the resultant tree is 2, 1, 3. Means we are rotating the tree like this, left direction once. So another, what is the balance factors? 0, 0, 0. Perfectly balanced. See, here one rule is, once we are rotating the tree, automatically the balance factors also, the binary search tree property also automatically set. Set means comparatively to 1 is less, 3 is greater. Okay. So whenever we are inserting one more element, say step 4, I am inserting one more element, that is 4. So 2, 1, here 3, here you are inserted as 4. Why? Because comparatively 2 greater, comparatively 3 also greater, so 4 inserted as a right child according to binary search tree. So we need to compute the balance factors again. So here the balance factor is 0. Here the balance factor is height of the left subtree is 0, height of the right subtree is 1, minus 1. Here also height of the left subtree is 0, height of the right subtree is 0, 0 minus 0, 0. Here height of the left subtree is 1, height of the right subtree is 2, so minus 1. So 0, minus 1 balance factors are allowed. So this is a balanced binary set. So this is the way to construct an AVL tree. This is the way to construct AVL tree. So each and every time we need to identify whether the tree is balanced or not. So the tree is not balanced. We need to check what kind of case it is, and we need to do corresponding rotations according to that. Okay. So in the insertion, we are getting totally 4 cases, 4 different kinds of cases. What are the 4 different kinds of cases? The 4 different kinds of cases are LL, LR, RL, RR. These are the 4 different kinds of cases. So according to the previous example, you know what it means. According to the previous example, you know what it means. What it means? So RR means whenever we are inserted a node in the right subtree as a right child, we are getting imbalance. That kind of case is called RR. Similarly, LL means whenever we are inserting a node in a left subtree as a left child, we are getting imbalance. That is the LL case. In case of LR case, whenever we are inserting a node in the left subtree as a right child, we are getting imbalance. That is called LR case. In case of RL case, whenever we are inserting in the right subtree as a left child, we are getting imbalance. That case are called as RL case. So here LL, RR, these two are single rotation cases. Single rotation cases. And LR, RL, these two are double rotation cases. These two are double rotation cases. Okay. So in the next coming slide, we are going to discuss about how we need to perform a single rotation, how we need to perform a double rotation. Right. So first, LL case. LL means left subtree as a left child. Left subtree as a left child. We are inserting, getting imbalance. That kind of case is called as LL case. So it is a single rotation case. What we have to do? Better example. Say 3, 2, 1. So 3 I am inserted root node, 2 I am inserted as a left child, 1 I am inserted as a left child. Why we are inserting like this? Comparatively 3, 2 is less as a left child. Comparatively 2, 1 is less as a left child. So we need to compute the balance factors. 0, 1. Why? Because height of the left subtree is 1, height of the right subtree is 0. So 1 minus 0, 1. Height of the left subtree is 2. Height of the right subtree, 0. So 2. So why I am getting 2 here means whenever I am inserting one node, I am getting imbalance. Means that in a left subtree, as a left child, you are inserted, you are getting imbalance. This kind of case is called LL case. What is the solution for this? Just rotating towards to right one time. Rotating towards to right one time. So how to balance in this? 2, 1, 3. Balance factor 0, 0, 0. It's perfectly balanced. This is LL case. This is LL case. So the next one is RR case. RR case means what? So in the right subtree as a right child we are inserted, we are getting imbalance. Perfectly reverse. Reverse example. 1, 2, 3. This is right skewed binary tree. So here the valence factor is 0. Height of the left subtree is 0, right subtree is 0, 0 minus 0, 0. So here minus 1. Height of the left subtree is 0, right subtree is 1, 0 minus 1, minus 1. So height of the left subtree is 0, height of the right subtree is minus 2. So minus 2 is the balance factor. So whenever we are rotating this, okay, we are rotating this, we are getting like this. So 2, 1, 3. So what is the solution for this? Rotation towards to left. Rotation towards to left one time. So we are rotating to left one time. So the balance factors are 0. Balance factors are 0. So this is the LL case, RR case. 2 are single rotation. Means that whenever we are performing rotation once, automatically you are getting balanced tree. Okay. The next case is LR case. LR case means what? So whenever we are inserted a node in a left subtree as a right child, you are getting imbalance. Left subtree as a right child, you are inserting a node, you are getting imbalance. Okay. So first left subtree. Left subtree means here 3 is there. 3 is there, but here 2. Right. So here not to write this now. So this is 1. This is 2. A small change. A small change. It's a binary history. Comparatively 3, 1 is less. Comparatively 1, 2 is greater. Comparatively 3, 2 is less. So it's a binary history. So we need to compute balance factors. 0. Here the balance factor is minus 1. Here the balance factor is 2. So again we are getting imbalance. So at this time, why we are getting imbalance? When we are inserting 2, we are getting imbalance. So what it means? In a left subtree, as a right child you are inserted, you are getting imbalance. In a right subtree, in a left subtree, as a right child you are inserted 2 element, that's why you are getting imbalance. So this is double rotation case. This is double rotation case. Double rotation means what? Rotation we need to perform twice. Rotation we need to perform twice. So what it means? First, this part rotation towards to left. This part rotation towards to left. Means first we are performing single rotation towards to left direction. Means we need to get the resultant tree is 3, 2, 1 like this. When we are perform the left rotation, we need to get 3 like this. So one rotation is over. You know what is the resultant rotation we have to do for this case? This is what type kind of case is? LL case. So what is the solution for this? We need to rotate towards to right. Means here we need to rotate towards to right direction. So right direction means what is the resultant tree you are getting? So 2, 1, 3, balance factor 0, 0, 0. So in this case, we need to perform twice rotation. One is first subtree part rotate towards to the left. Then the total tree part rotates towards to right. So this kind of case is called as R. Finally, I will move to the last case, that is called RL case. I think you automatically guess what is RL case. When we are inserted a node in a right subtree as a left child, we are getting imbalance. Right subtree as a left child, we are getting imbalance. So directly I am moving for an example. What is the example for this? Okay. Say, so 1 is there. 1 is the root node. The next right subtree. So here I am inserted 3. 2 is a left child. What are the balance factors? So here the balance factor is 0. Left subtree, height of the left subtree is 0, right subtree is 0, 0. Here 1, height of the left subtree 1, right subtree is 0, so 1 minus 0, 0. Here height of the left subtree is 0, height of the right subtree is 2. So that's why 0 minus 2, minus 2. So again I am getting imbalance. Here I am inserting, newly inserted node is 2, but the insertion performed in right subtree. So in the right subtree as a left child I am inserted, I am getting imbalance. So this kind of case is called RL case. Here also we need to do double rotation. So what is the rotation? First rotation towards to right. Means what is the tree, resultant tree you are getting? 1, 2, 3. When we are rotating this tree towards to right, 2 becomes parent node, 3 becomes child node. The resultant tree is like this. You already seen that kind of case. That is RR case. So how to balance this one? We need to rotate in left direction. Means the resultant tree is 2, 1, 3, balance factor 0, balance factor 0, balance factor 0. So this is balanced. Where you have performed 2 rotations here, the subtree part you are rotated towards to right, the entire tree you are rotated towards to left. That is called 2 rotations. Once you have performed 2 rotations only, you are getting balanced. So these are the totally 4 different kinds of cases you are inserting a node in the AVL tree. So finally, I am coming to the conclusion, summary part. So in the today's session, we have discussed balanced binary search trees. Balanced binary search tree. What it means, balanced? Balanced means we need to find out the balance factor. The balance factor values are allowed only -1, 0, 1 in case of AVL tree. So here we have seen as one kind of tree that is called AVL tree, that is only in your syllabus. And in addition to this, I already discussed what are the other type of trees. Types of balanced binary search trees, that is red flag trees, splay trees, big trees, that is already in your second semester syllabus, advanced data structures. In third one, we have discussed about operations in AVL tree. Fourth one, just in the insertion operation, given a small example, what is the need of rotation I explained. After that, I explained 4 different kinds of rotations, that is LL, RR, LR, RE. LL, RR, these 2 are called as single rotations. LR and RL, these 2 are called as double rotations. So in the next session, we will go to discuss one example related to insertion again, and later we will discuss about deletion manually. Then finally we are going to look at the pattern. Thank you.